My name's Samir Khan, and I'm the Professional Market Product Manager for Maple. Today, we'll spend some time talking about signal processing. We'll discuss the tools and features in Maple for signal processing, where Maple stands for the competition, and we'll walk through some applications. And it's the latter point that I get really excited about, real-world analysis using tools like Maple. To go with this webinar, we've developed a range of applications that demonstrate signal processing techniques in Maple. There's a lot of stuff here. There's a wide range of applications which touch on many different subjects, and we'll walk through some of these later. This one, for example, denoising an image, demonstrates how you can remove noise from a signal using thresholding with fast Fourier transforms and wavelets. This application is pretty interesting. It demonstrates how you can estimate the spectra of irregularly sampled data. And specifically in this application, we use that concept to predict the existence of an exoplanet. This application demonstrates how you can design a pyramidal antenna using Maple's numeric solvers. All of these applications are available on the Maple Application Center. So if you go to maplesoft.com/applications, you can download all of these applications. So let's look at the bigger picture. I'll go into a little bit more detail on Maple signal processing tools on the next slide. But there are lots of them. There are lots of signal processing features. You can import and export many different types of data, so spreadsheets, CSV, images, text, audio, binary data files. Maple has a long heritage as a symbolic math tool, and that helps you understand academic concepts such as convolution. We have unit-aware numerical solvers which allow you to solve iterative problems. And as we've demonstrated, we have many examples and applications for you to explore. So what can Maple do for signal processing? Well, as I said, there's lots there. They're in the signal processing package, and there are supporting tools in other packages as well. There are features for signal pre-processing and generation, so smoothing, denoising, outlier removal, resampling, interpolation on both regular and irregular grids. There are filter design tools. There are various transform methods, so FFTs, discrete cosine transforms, wavelets, real and complex cepstrums, and more. There's a number of spectral analysis tools, so periodograms, spectrograms. You can also generate Lund-Scargill periodograms of irregularly sampled data. There are many signal manipulation and arithmetic tools for convolution, cross-correlation, autocorrelation, peak finding, signal statistics, and much more. There's a lot of miscellaneous tools in all of these supporting packages for generating phase magnitude plots, curve fitting, multivariable regression, symbolic math tools, transfer functions, state space models, differential equations, optimization, and more. And as I mentioned on the previous slide, you can also import and export many different types of data as well. So where does Maple stand in relation to the competition? Well, Maple's traditionally been known as a computer algebra tool, and that's a fundamental part of its heritage. And many engineers have used Maple at university in their calculus classes to solve differential equations and integrals. However, there's also a significant number of numeric computation features in Maple as well. One aspect of which are tools for signal analysis and processing. So why would you want to use Maple instead of other tools such as signal processing? And by traditional, I mean command line oriented tools like MATLAB, as well as high-level programming languages like Python. I've also known many people use Excel for signal processing, and frankly, that's a really bad tool for that topic. Now, many traditional signal processing tools are essentially coding environments. The commands, the codes, are essentially programs, and if you want to document the code, you have to do it separately in a word processor or write code comments as well. There's no richness to that. Any plots are given in separate windows. In short, there's little feedback between the context of the application, the commands, and the results, the plots. Now, continuous smooth flow feedback is critical to increase productivity, especially if you're developing new algorithms or just exploring the solution space or just exploring concepts at the academic level. There are also questions about the maintainability of programs written like this. It's difficult to pass them on to other people who work in a team because it's certainly more difficult to get a sense of the conceptual flow of the program. So, what does Maple offer? Maple Document fundamentally is a much richer environment. You can include equations in natural math notation. You can include explanatory, fully formatted text, just like a word processing environment. You can copy and paste in pictures, other elements. You can use tables to fine-tune the layout of a Maple worksheet. This means you essentially capture the assumptions, background information, as well as the calculations. I'd also like to highlight the quality of Maple's visualizations as well. It's easy to produce a simple plot, but with a little tweaking, you can produce some very, very visually impactful plots and charts. And you can finesse the look and feel of the plots right down to the precise color grading of the color range on the spectrogram. The plots and visualizations are in line in the worksheet, and that gives you a closer connection between the algorithm or the code you're developing and the results. So let's switch into Maple and look at a number of these applications. So I'm going to assume that everyone has a basic knowledge of Maple, so this won't be a basic Maple tutorial. We're just going to walk through a number of applications, talk about the concept, and that hopefully should give you a better understanding of the value that Maple will give to you. So here I have a launchpad of applications. We'll go through 2 or 3 of these, covering various concepts. Let's start off with this one, signal denoising. So in this application, we're going to denoise a signal with wavelets and FFTs. So we start off by defining a noisy signal. And this could be data I've imported, but for the sake of this application, I've simply defined a signal that consists of 2 sinusoids, and I've added random noise. And this is what the signal looks like. So let's say that we want to try to remove some of this noise, try to get a smoother looking signal. Well, I'll show you how you can do that with wavelets and FFTs. Now, wavelets are a pretty interesting concept, and there are various classes of wavelets. This function implements hard wavelets. So we define a thresholding value. We calculate the discrete wavelet transform of our noisy data set, and then we do some thresholding. If the content of the discrete wavelet transform is lower than the threshold value, we zero it out. Otherwise, we leave it alone. We then calculate the inverse wavelet transform and plot the results over the original noisy signal. And as you can see, we've done some smoothing. Now, if I were to change the thresholding value and recalculate the worksheet, it would change the filtered signal. Now, we can do much the same with FFTs as well, fast-forward transforms. Again, we use this function, FFT, to calculate fast-forward transform of our noisy data set. We then threshold the data. We then calculate the inverse FFT and plot the filtered data over the original noisy data. So as you can see, we've smoothed out a lot of the noise. Now, there's an interesting feature that we introduced into a recent version of Maple. You can actually export plots in SVG format. So if I right-click on a plot and select Export, SVG, this allows me to export a plot in SVG format. Now, SVG is a vectorized plot format that remains crisp and clear at any zoom level. So if I zoom in, you can see the text and all the lines remain crisp and clear. So let's go back. Let's look at another application. Now, as well as applications which expose the commands and the mask, you can also create applications like this. Here we don't see any commands, we simply have buttons, drop-down menus, radio buttons, and text boxes. And these plots also contain some interactivity as well. We can load a wave file, let's say this one, and plot the spectrogram, waveform, and the periodogram. So let's say that we wanted to apply a filter to this audio file. Well, I can do that easily with my interface. So let's select a finite impulse response filter. We'll stick with the standard low pass filter. And just to demonstrate the interactivity that you can achieve with a Maple application like this, you can click on this plot to set the cutoff value for the low pass filter. And that value is automatically reflected here. If I process the data, you can see the difference it makes to the spectrogram. Do that again. There you go. So one of the final two applications I want to show you is this one. This is actually a pretty interesting application which demonstrates Maple's tools for estimating the power spectra of irregularly sampled data. So we have some astronomical data which is irregularly sampled. In this instance, the astronomical data is the radial velocity of a star. let's import this data and plot it. So on the y-axis, we have radial velocity. On the x-axis, we have the Julian days. Now, as I said, this data is irregularly sampled, so we can't use traditional Fourier-based techniques to estimate the spectra of this data. We have to use other algorithms. One possible approach is a Lumsgoggle periodogram. Well, we can use this function in the signal processing package and give it our time data and our radial velocity data. Plot the results and we get this. An estimate of the power spectral density on the y-axis against the period, the inverse of the frequency on the x-axis. Now, this particular data shows a strong peak here at around 62 days. This strong peak is actually evidence of the presence of an exoplanet around this particular star. Now, as well as audio files and data files, we can also analyze images using signal processing techniques as well. Let's look at this application. Here we're going to remove some noise from an image. So we're going to start off by importing an image. And this is actually a photo of the Maplesoft office building in Waterloo, Ontario. Now, quite often when you take digital photographs, the resulting photo can often be polluted with noise due to sensor noise or irregularities in the processing technique. A common type of noise is periodic noise like this. And we can process and remove this periodic noise with fast Fourier transforms. Now we can take the Fourier transform of an image to move it from the spatial domain to the spatial frequency domain. And again, all we need to do is use the FFT function. And this is what the image periodogram looks like. So we've gone from the image domain here to the frequency domain, the spatial frequency domain. So we see two peaks here, one peak here and one peak there. And that's typical of periodic noise. What we can do now is try to blank out this noise. So wherever we see peaks here, we can zero out. So I'm going to take the data, the spatial frequency data, and zero out a certain block, these particular values. And I think that will roughly correspond to a square over this peak and a square over this peak. So let's embed that. And let's see what the resulting periodogram looks like. So this is the image periodogram after I've applied my notch filter. You can see that I've zeroes out this data here and this data here. So now we're going to take the filtered data and calculate the inverse FFT to take it back from the spatial frequency domain to the image domain. And this is my processed image. As you can see, I've removed a lot of the periodic noise, although I think some of it is still present at the edges, but the image looks a lot cleaner. So there are many other applications that you can explore. On the application center, we have applications which demonstrate how you can compress audio using discrete cosine transforms. We have applications which demonstrate how you can apply high resolution frequency estimation to a signal. And there are also applications which demonstrate the value of Maple's symbolic math tools to signal processing as well. So in this application, we're examining coded excitation signal analysis. And I won't run through this, but this application relies on Maple's symbolic math tools to generate large symbolic results and animations. So all of these applications are available on the Application Center at mapletop.com/applications.